This presentation explains the stress behavior of blast furnace hearth shell during blow-in and after an extended outage. The study covers BF1 and BF3, aiming to prevent hearth breakouts by understanding the stress contributors. Now we compare two furnaces BF1 and BF3. Both have a hearth diameter of 10 meter. BF1 has a shell diameter of 12.94 meter and uses semi-graphite EHM refractory with hearth safe cooling. BF3 has a slightly smaller shell of 11.99 meter. It uses a semi-graphite EHF refractory and and surface shower cooling. Now the goal is to study the hearth shell stress during blowing period. We aim to detect factors that cause stress and explore preventive uh, strategies to avoid breakouts. Now coming to the strain gauges that were installed in two row, 8 per row on the hard shell of BF1 and BF3. BF1 was cleaned before blowing and had no salamander. BF3 had a fully developed salamander which influenced the stress behavior as it is well shown the both figures of BF3 and BF1. Now coming to the images shows where the strain gauges were installed on both furnaces. The layout helped us capture the stress distribution during a startup phase. Now in BF1, stress peaked at 100 MPa on day 5 and then stabilized to 30 to 40 MPa by day 14. BF3 showed higher stress 160 MPa by day 7, setting to 30 to 50 MPa by day 23. The highest stress were observed opposite the taphole, indicating non-uniform distribution. BF3 experienced greater stress due to shell refractory contact and salamander presence. So this is a good outcome that when it has a more salamander, I mean it has a salamander retention in the heart, then we have a more greater stress as far this study is concerned. Now critical finding of the alarm level, as we know that refractory expansion uh, mm, and it is refractory expansion and not salamander is the key driver of cell stresses. Stress reduced once thermocouple reached creep temperature. Threshold levels were defined for BF1 and BF3. Stress below 165 MPa uh, mm, is to be monitored, and displacement above 34 to 37 mm we have to reduce blast pressure. So these are the basically easily recommended um, ways which can help in mitigating and taking a uh, fast solution. So recommendation and future work during this blow-in, we can say that controlling the two-year opening speed, casting schedules, and melting rate to reduce stress is also a skill and is to be also met in order to relieve the hearth from stress and stress. Use hearth thermocouple to identify creep temperature accurately. This is also important. We have to avoid the cracks in refractory during outages. Future tests will focus on optimizing heat input for better stress absorption also. So now this diagram illustrate how the stress is relieved through refractory creep and designing your presentation. Use red for this is the color coding sort of thing. Use red for BF3 and blue for BF1. Highlight important values like 100 MPa, 160 MPa. This is basically a sort of a diagnostic tool which can navigate or guide us in order to have a proper